Hello, I'm Ivan, and today we will consider the topic robustness of AI algorithms for neurocomputer interfaces based on software and hardware technologies. So this slide presents the content of our presentation. First, we will look at the importance of bionic devices. Then we will proceed to the description of the experiment. Next, we will explain the research process itself, and finally demonstrate the obtained results. So let's move to the discussion of programs for bionic devices and play an important role in modern life. First, bionic devices significantly enhance the mobility and independence of individuals with limb loss, allowing them to perform daily activities with greater ease and confidence. Secondly, bionic programs use adaptive learning algorithms to personalize and enhance the functionality of bionic devices over time. The investigation goal was to use machine learning methods to analyze encephalography signals obtained during patient motor activity. Also, we evaluated and compared the robustness of each machine learning method to determine its effectiveness. We chose a 16-channel computer encephalography complex neurocom for the analysis of brain encephalography signals. For our research, we conducted an experiment in which the encephalograph was worn on a patient to record signals from the brain. During the recording process, the patient performed movements of finger combinations. This action allows us to collect the necessary data for further analysis using machine learning methods. After the experiment, we received several files with encephalography signals. In the picture, you can see how the received data looks like. Each line in each file represents a recording of encephalography signals at a specific point of time in time. Yeah. Mathematical modeling for movement prediction is the use of machine learning methods to create a model that can predict movement based on input data. This process includes several key stages. The first stage, model selection. We have to select the appropriate machine learning model that is the best suited for movement prediction. Second stage is model training. Here we are using training data to train a machine learning model. And finally, the last stage is model evaluation. Here we check the accuracy and robustness of the model on test data. Let's take a look at the evaluation flow of machine learning methods. First of all, we merge all the received encephalography files into a single dataset. Then we create an instance of an appropriate classifier from the scikit-learn library. After we perform cross-validation by passing the instance and merge dataset, we can evaluate the model of different subsets of input data and obtain multiple accuracy for each matrix. Then we calculate dispersions for each metric based on obtained accuracies. Finally, we find the models of the vector of dispersion obtained for each matrix. In the end, we obtain the general dispersion that will characterize the robustness of the mathematical model. In our research, we use the Python programming language, includes the following packages: pandas, numpy, matplotlib, pyplot, collections, and scikit-learn. We use scikit-learn, and it is a powerful library because it has all the necessary classifiers implementations. We used back-end boosting nearest neighbors and support vector classifiers to analyze encephalography data. Each of these classifiers has its own unique features and way of working. To standardize dataset, we use a standard scalar class from the scikit-learn library. After that, we split the set as 3 to 1, where more of the data is used to train the machine learning methods and less is used to test their performance. As you can see from the picture, the data in each dataset is randomly selected. Let's take a look at the result of back-end machine learning method. We obtained the following dispersion result, which you can see on the slide. Also, we created a normalized confusion matrix. This matrix gives us a better understanding of the possible classifications results and help us to understand how well the model recognizes each class. From this matrix, we can conclude that in general, the accuracy for each class is not the same. We can see that for the classes responsible for the movement of two fingers, the backend classifier showed slight lower results compared to the other classes. Now let's look at the result of near neighbors machine learning methods. We obtained the following dispersion result, which you can see on the slide. So we additionally formed a normalized confusion matrix. From this matrix, we again got a similar result as with the previous matrix. We got slight worse accuracy for the movements of two fingers. Next, we will consider boosting machine learning method. Here we can see the result of the results on the slide. We also created a normalized confusion matrix. Here we can see the accuracy for each class is very low. Is very small in contrast to the previous matrix. And finally, we will consider the support vector machine learning method. We can see the calculations result on the slide. From the normalized confusion matrix, we can conclude that the accuracy of detecting or the movement of one finger is higher than the of other combinations. And last, after the calculation, we obtained the general dispersion for each classifier. From here, we can make the following conclusions. The nearest neighbors classifier shows the lowest dispersion, which indicates its higher robustness, and the lowest spread in the measured matrix. This means that it shows more stable and reliable results compared to other classifiers. The backend classifier is the next in terms of robustness, which also showed a fairly low level of dispersion, but slightly higher than that of the nearest neighbors classifier. However, the difference is very small. The support vector classifier shows slightly higher dispersion, which may indicate less stability in its results compared to other classifiers. Finally, the boosting classifier shows the highest dispersion, which may indicate the largest spread of the results and the least robustness compared to the other classifiers. Moreover, the accuracy of this classifier is in this experiment was extremely low. We recommended using nearest neighbors or backend classifiers, choosing from the 4 classifiers that we proposed to ensure the best robustness for solving the task of recognizing finger movements from encephalography signal data. So, thank you for the attention.